Okay, so last lecture I talked about the registers. Okay, so we have seen the register and how we can implement the register. Okay, so we can have an n-bit register, which is implemented using n flip-flops. So we connect the clock to all of these flip-flops, to the clock input. The register can have a load enable. The register can be a shift register. It can have a serial input. We have seen different types of shift registers. We can shift to the right, we can shift to the left. You can actually have a serial input. You can also have a parallel input. You can have a serial output. You can have a parallel output. We have seen the also universal shift register. So all of these are like just variations, okay, of a register. We also have seen how we can use this in some examples, design examples. So we have seen, for example, how we can implement a sequential adder and how we can add the bits sequentially, starting at the least significant bit. And we can save the carry out, and I can use it a carry in for adding the next bits. And then I can save, okay, the sum bits in a shift register. And then after repeating n times for all the n bits, we can output all of these n bits in parallel at the output of a shift register. So therefore, we can shift this, we can save this sum, and we can output the final sum. So this is good. Okay, so we can design, okay, sequential adder, okay, in this way. Right. Today will be about counters. Counter is also a very important sequential circuit, which is used a lot in sequential circuits. So when you are designing a digital system, people use counters. And we can use a counter, let us say, for counting the cycles. We can use a counter for counting events. Okay, for whatever reason that you would like actually to, whatever you'd like to count in your circuit. So how do we design a counter? So the counter is a sequential circuit, and it goes through a specific sequence of states. Now, if you recall from my last, not my last presentation, in fact, before that, when I was talking about state diagrams, you can design the counter as a state diagram, and you can obtain the equations using, let us say, the Carnot map. But we are not going to do it we are not going to do it this way this time. We are going to do it differently. So, so you can design the counter the traditional way, or you can do it as I'm going to describe in this presentation. Okay, so so the output of the counter can be n bits. So that's here my counter. So all what we need in the case of a counter, okay, so let me use my highlighter. I need a clock. So cycle by cycle, first I need a reset. So this reset, okay, can reset my count initially to 0. So we start initially in count 0. So that's the importance of reset. And also we need a clock. Okay, so the clock is essential, because cycle by cycle, I'm going to change the value of the counter. So, so that's basically is my counter. That's it. That's what I need, okay, to design a circuit that basically does counting. So in this example, I'm going to count the number of clock cycles. Notice that it's called a modulo n counter, modulo n, which means that here we count from 0 to n-1, and then back to 0. That's called a modulo n counter. So we start 0, 1, 2, etc. until I reach the last count value, which is n-1, and then we go back to state 0, in which the count is equal to 0. So we go back to count 0. Okay, so that's here my modulo n. For example, you can have a modulo 8 binary counter. So we count in binary. So we go from 0 to 7. And once we reach 7, we go back to state 0. Right. If I have a modulo 8 binary counter, how many bits do I need for my count? How many bits? Or how many flip-flops do I need?
3 flip-flops?
Yes, thank you very much. 3 flip-flops. Because with 3 flip-flops, you can actually have 8 states, and these states can be from 0 to 7. In binary, it will be 0, 0, 0, and then the last state will be 1, 1, 1. So therefore, we can count from 0 to 7. And once you reach state 7, you go back to state 0. Okay? Right. So So in this example, if you use a modulo 8 binary counter, then this n here, which is shown here for the number of wires for the output count, will be only 3. It will be only 3 bits. That's it. If you have a modulo 16 binary counter, how many bits you need for the count and how many flip-flops? If you have a modulo 16, 4, exactly 4. So basically, you need log base 2 of the number of. So basically, if you have a modulo n, capital N, then the small n here, which is the number of flip-flops or the number of wires for my count, will be log base 2 of capital N. Okay. So here, actually, the n here indicates the small n indicates the count value in binary. Okay, so if you would like to have modulo 16, you will count from 0 to 15. So you need only 4 bits, only 4 bits. So this is log base 2 of 16 is equal to 4. So you need only 4 bits to count from 0 to 15. And once you reach 15, which is 1, 1, 1, 1, 4 1 binary, you go back to 0. That's a modulo 16 binary counter. Now, if you would like to have a BCD counter, in the case of BCD, we call it modulo 10. So I'm not going to count all the way to 15. I'm going to count from 0 to 9 and then back to 0. That is called a BCD counter. Okay. So, so we reach 9. I'm not going to count to 10 to 15 and then back to 0. No, I'm going to skip all of these and go back direct to 0. So 0 to 9 and then 0. Back to 0. So this will be called a BCD counter. It only counts from 0 to 9. These are the BCD digits. Right. If I would like to have a BCD counter, a modulo 10 counter, how many bits do I need for the count value for my output count? How many bits do I need? Again, 4, yes. Again, 4, yes. It's like the modulo 16, okay, but modulo 10 also needs actually a 4-bit count. But we're not going to use all the possible count values. So there are states that we're not going to reach. So here we can go from state 0 to state 9, but from 10 to 15, we're going to skip them. And we can go back to state 0, okay, where we have 0, 0, 0, 0 is the output. So it's like the modulo 16, except that we don't count from 10 to 15. Halas. We just skip all of them and we go back to 0. Okay. Now, another thing about counters is that we can count either up or down. Both are possible. Yeah, and you can count, let us say, from 0 to 9 and then back to 0, or you can start at 0 and then go down to 9 and then all the way down to 0. So 9, 8, 7, 6, okay, and so on. So until you reach the 0 and then back to, so basically you can count backwards, down. So there are 2 ways of counting, either up or down. And you might encounter both in design. People use counters for timers, okay, just to keep track of time. You can just use counters. Or for event counting, every time you have an event, you count it. Or let us say in the case of frequency division, okay, so you can actually use it to divide the frequency of a given clock cycle. I'll talk about these different applications of using a counter. But that's basically is the counter. Now, how do you implement the counter? I will show you different ways of implementing the counter. We can actually have 2 basic approaches. One is called the ripple counters. Okay, and the second one is called the synchronous counters. So these are the basic approaches for implementing counters. In fact, people actually have invented different types of counters. You will actually encounter them in your chapter, okay, about registers and counters. There is actually a chapter in your textbook about this. Okay, so these are different implementations, how you implement counters. Okay, now let me talk about the ripple counters first, and then I'll come back to synchronous counters in great detail. And I will show you how you can implement BCD counters and other types of counters. We'll talk about all of these. Now, in the case of ripple counter, why people like, what's the advantage? It's a very simple circuit, and it has a low power consumption. The thing about ripple counter is that They are really simple to implement. Very simple to implement. This is the main advantage. So here the advantage is that it's a very simple circuit, and it does not really require a lot of power consumption. So it consumes little energy. Okay. Now the disadvantage is that it's not truly synchronous. It's not really synchronized with the clock. Okay, so not all the flip-flops are connected to the same clock. And that is a big problem about triple counters. So really, the implementation is very simple. We take the flip-flop output. It is connected to the clock input of the next flip-flop. That's basically the ripple counter. And I will show you how this is implemented in great details in the next few slides. Okay, so the problem is that there is no common clock which is used by all flip-flops. So the clock is not connected to all the flip-flops. And because of this, it's not truly synchronous. Okay, and this is there is also a problem, which is the propagation delay. Abdul Malik, you have a question?
Yes, Doctor, about the disadvantage. This will result in error in counting, right? Not
errors, but actually in delays. So it will actually, I'm going to show you exactly how you, okay, I'm going to show you the details about this ripple counter. Just wait for the next few slides. Okay, so the problem is the propagation delay. Okay, like in the case of the ripple adder, we had the propagation delay, and this propagation delay is going to increase as we go from one bit to the next bit. The same thing in the case of the ripple counter. Okay, when you go from one bit to the next bit, this is going to increase the delay. So this is why it's not truly synchronous, and the clock is not connected to all the flip-flops, and that's actually is a problem. So, so it's simple to implement, but this is the main disadvantage of ripple counters, and this is why people sometimes don't like them. Okay, although they actually are very simple to implement. On the other hand, the synchronous counters, all the flip-flops are connected to the same clock. So the clock is going to be connected to the clock input of all the flip-flops. It's very important that we are using a clock that we connected to all the flip-flops, because we'd like to change all of them at the same instance of time. Okay, at the same instant of time, at the same edge of the clock. So this is why it's truly synchronous, because all the flip-flops are synchronized with the same clock. Now, in order to go from one state to the next state, we use combinational logic. That's it. Okay, so basically we just increment the count or we decrement the count. So we use actually combinational logic, which is basically needed to implement the next state, the desired sequence of counts. Okay, state sequence. Right, let me start first with the ripple counter, just to clarify what I mean by that. And then later I'll come back and talk about synchronous counters. Now, ripple counter is shown here. This is an example of a counter. I'm using 4 flip-flops. You can use any number of flip-flops, by the way. I'm just showing a 4-bit counter. So basically here, my count, remember in the case of the counter, the Q output is the count value. Okay, so here notice that we have 4 bits. We have 4 flip-flops. So we have here 4 outputs, Q3, Q2, Q1, Q0. Okay, this is basically my output. This is the count value. Because we have 4 bits, we can count from 0 to 15. So 0 means 0, 0, 0, 0 in binary. And 15 means that we have 1, 1, 1, 1. That's 15. So we can count up from 0 to 15. And once we reach 15, we go back to 0. Right, let us understand this counter. It's really easy to understand. It's not really that complicated. Okay, now notice that here I'm showing from 0, 0, 0, 0 in this table up to 1, 0, 0, 0. The reason why it goes to 15, it does this, I'm showing here from 0 to 8, but really there is no space to show in this slide to show to 15. I will show it in the next slide, inshallah. I'll come back to it. Okay, so I'm drawing it, by the way, I'm drawing it vertically, but in the textbook, probably they are drawing it horizontally. So I'm just using my own drawings, okay? But it's the same. It's just exactly the same ripple counter. Let us understand this. Now notice that the clock here is connected only to the least significant. This is the lower bit. Okay, only to bit 0 that outputs Q0. Okay, so that's the clock. It's not connected to the other flip-flops. No, it's only connected to one flip-flop, which is bit 0. So notice that how it works. Okay, I have a reset. Now the reset is connected to all the flip-flops. There is an R input here. That's my reset input. I call it reset. Okay, so if you would like to reset, you are going to reset all the flip-flops at the same time, and therefore you get 0, 0, 0, 0. That's my reset. Now notice the clock is connected only to bit 0. Right? Okay, what does it mean? Well, it means that we only change Q0 at the edge of the clock, at the rising edge of the clock. Only Q0 is changed. But how do we change Q0? Notice that Q0 prime, this output is connected. Notice the way that I'm wiring it. Okay, there are no gates. We are just taking Q0 prime and connecting it to D0. Like initially Q0 equal to 0, right? So if Q0 equal to 0, then Q0 prime will be equal to 1. So we're connecting 1 back to D0. Now the next cycle, at the next edge of the clock cycle, then Q0 becomes 1. Forget about the upper flip-flops. Just focus on Q0. Just focus with me on Q0. So initially Q0 equal to 0. Then next cycle is going to become 1. Why? Because we are connecting Q0 prime back to D0. Okay? So now this becomes, so next cycle at the next edge of the clock. So notice that this is a flip-flop. So therefore it's going to change its state at the edge of the clock. Now next cycle is going to become 1. Okay? So when Q0 becomes 1, Q0 prime becomes 0. So we connect 0 back to D0. So next cycle is going to become 0. Then 1, then 0, then 1, and so on. So that's basically is a Q0. So notice that it's actually toggling 0, 1, 0, 1, 0, 1, 0, 1. That's basically is Q0. Right now, let us understand Q1. Okay. So remember that here Q0 is going to toggle. Toggle, it means that's going to invert. Yani it's going to change from 0 to 1 or from 1 down to 0. So this is the meaning of toggling. Toggling means it's actually inverting its value, changing from 0 to 1 or from 1 to 0. So this will happen at the positive edge of every cycle. Cycle by cycle, we change the value of a Q0. That's it. Okay? Fine. Let us understand Q1. Okay, I need actually maybe to use my pen tool. So notice that Q0 prime here, this Q0 prime, is connected not only to D0, but to the clock input of Q1. What does this mean? What does it mean to have the Q0 prime connected to the clock input? So it's not the clock which is connected to the clock input, it's Q0 prime which is connected to the clock input of Q1, of this flip-flop. What does it mean to have a Q0 prime connected to the clock input of this flip-flop one that has its output Q1? Let's understand this. Now remember that we change the value of a Q1 at the rising edge. So initially Q1 equal to 0. Okay. Now we're going to change the value. So notice that this is a Q0 prime, not a Q0. So when a Q0 equal to 0, then it will be 1. And when it's 1, Q0 prime will be equal to 0. So when a Q0 goes from 1 down to 0, it's Q0 prime going from 0 to 1. So this will be the rising edge. Then in this case, we toggle the value of Q1. You understand this? So notice that I'm connecting Q0 prime to the clock. So therefore, when Q0 changes from 1 down to 0, then Q0 prime is jumping from 0 to 1. It is just the complement of Q0. And therefore, because we have here a rising edge, then therefore it's going to see the edge as if now a Q0 prime is acting like a clock. and therefore is going to change the value of Q1 from 0 to 1. Right. Let us understand here. Okay, so that's what's really happening in the case of a Q1. So notice that Q1 prime, this Q1 prime, is connected back to D1, and it's connected to the clock input of Q2. It's the same wire which is connected. So let's understand this. Okay, so now when we have Q1 going from 1 down to 0, then basically Q1 prime is going from 0 to 1. So this will be like the edge of the clock, and the Q2 is going to go from 0 to 1. So notice that in the case of a Q1, we get 0011, 0011, and so on. In the case of a Q2, we get 4 zeros followed by 4 ones. And in the case of a Q3, we get 8 zeros followed by 8 ones. I have it probably more clear in the next slide. Okay, let me show it to you. Okay, this is actually better explained in this slide. Right. So now I'm showing here all the 16 possible count values, starting at 0000 and ending at 1111. Okay, this is my ripple counter. Okay, right. I don't know whether to use a highlighter or let me keep my pen tool. So notice that initially they are all zeros. So when I reset, I start in the start state, which is 0000. So this is where I start. Okay. Now, because we are connecting Q0 prime here, Q0 prime, we are connecting it back to D0. And this clock is ticking. So at the rising edge of the clock, Q0 was 0, it becomes 1. And then if it is 1, it becomes 0. So basically, we are toggling the value of a Q0. We are toggling the value of a Q0 cycle by cycle. Okay, that's for a Q0, it's easy part. Now let us understand Q1. We are connecting Q0 prime to the clock input. This is my clock input here for Q1. I'm just repeating myself. So therefore, when you see here that Q0 going from 1 down to 0, I'm showing here next to it that Q0 prime is going from, sorry, let me clean up this. So notice that here I'm showing Q0, I'm showing Q0 prime. So when a Q0 goes from 1 down to 0, Q0 prime is going to go from 0 to 1. It is just the complement of Q0. Now, Q0 prime is used as a clock for a Q1. So therefore, this is like a rising edge of a clock. And therefore, Q1 is going to change at the rising edge. So what is the value of, okay, D1? The value of D1 is just a Q1 prime. So the value of Q1 prime, so the value of Q1 is 0. The value of Q1 prime is 1. So this is going to change from 0 to 1. So it's going to change from 0 to 1 when a Q0 goes from 1 down to 0, or when a Q0 prime goes from 0 to 1. Okay? You can see that this is also happening here when a Q0 prime going from 0 to 1. Notice that how this is actually toggling. So therefore, it's toggling here. It's toggling here, right? So it's toggling every 2 cycles. Okay, we are changing the value of a Q1 to become a Q1 prime. So notice that we are taking Q1 prime here and connecting it back to D1. So this is actually, we are doing it like this so that we can toggle the value of Q1. So Q1 actually is 0. It will remain 0 for 2 cycles. And then after that, we change it to 1. It's going to remain 1 for 2 cycles, and so on. That's actually is for Q1. Okay. How about Q2? Now notice that in the case of a Q2, we toggle when a Q1. Notice that Q1 prime is connected to the clock input here for a Q2. That's actually is a Q1 prime, okay, which is wired here. So therefore, when a Q prime, if you look here at okay, if you look here at Q1 going from 1 down to 0, this is when Q1 prime is going from 0 to 1. So this is when we toggle the value of a Q2. Okay. So Q2 will be 4 zeros for 4 cycles, and then it's going to toggle here. So only when Q1 prime goes from 0 to 1. It's here, it's here. That's when we toggle. And it is here. So this is how we toggle. Okay, we toggle, it means that we invert. We invert, yani we change it from 0 to 1, or we change it from 1 down to 0. Okay, that actually means toggling. That's how the counter works. And in the case of a Q3, that's the output. This is for the this is the upper bit here. Notice that how Q2 prime is connected here to the clock input of Q3 to this clock. So notice that here Q2 prime is going to change from 0 to 1 here. So that's actually when we change, we toggle Q3. Okay. Also is going to toggle here at the bottom, but it's not really shown. So it goes from 0 back to 1. That's also is going to toggle. Okay, the value of Q3 will go back from 1 to back to 0. So once we reach 1, 1, 1, 1, all the bits will go back to 0, 0, 0, 0. Okay, so I'm showing here both the Q and the Q prime. So notice that in the case of a Q, we are counting up. So we start here at, if you look here at the toggling, basically we are counting up. So we start at 0, 0, 0, 0, then 0, 0, 0, 1, then 2, 3, 4, 5, 6, 7, all the way to 15. So we're counting up. If you look at Q prime is just the complement of a Q, because every flip-flop has a Q and a Q prime. So notice that when a Q equal to 0, this will be 1, 1, 1, 1. So we start at 15, and then 14, then 13, then 12, and so on. So we're counting down from 15 down to 0. So when the Q counts up, the Q prime counts down. So basically, we're achieving count up and count down using the same counter. Okay, so remember that Q0 prime is used here. This Q0 prime is used as the clock for Q1. Q1 prime is used as the clock, okay, for Q2, and the Q2 prime is used as the clock for Q3. This is basically the wiring which is done in the case of a ripple counter. Okay, any question about this? Right, I spent some time explaining the ripple counter. Notice that if I would like to count down, if I would like to reverse it, and I would like to have the Q counting down and the Q prime counting up, I would like to reverse this. How do I do it? Any idea? If I would like to change the count down,
by
taking the Q0 to the clock.
Yes. So basically, we connect the keys exactly. So we connect here Q0 to the clock of a Q1. We take a Q1 to the clock of a Q2. Now we still connect Q0 prime to D0 and Q1 prime to D1 because we have to toggle. But we take a Q0 to the clock of a Q1. We take a Q1 to the clock. So I have to change the wiring. Okay, I have to change the wiring for the clock input. So the clock of a Q1 has to come from Q0. And the clock of Q2 has to come from Q1, not from Q1 prime. So if you do it like this, then basically you make all the Qs to count down and the Q prime to count up. So basically we're reversing them. So you can do that if you want to. Yes, of course, you can actually have different counters. Okay, one that will count up, one that will count down. Okay.
But how about the reset? How can I get 1, 1, 1?
No, reset itself, reset means it's going to force all the outputs to be zeros. That's the reset. Okay. So you start here at zeros. So once you start at zeros, right? If you are counting down from zeros, you can go to 1, 1, 1, 1. Okay. That's the reset. So reset means that initially you initialize the output, the state, you initialize the state to zeros. And then if you would like to count down, once you have zeros, you can actually go down to 1, 1, 1, 1. Okay, so you go from 0 to 15 to 14 to 13 and so on. That will be counting down. Okay. So how can you get from 0 to 15? Is this the question? Just actually wire them differently. In fact, notice that here, Okay, in the case of the Q, let us just look at the Q prime. If you see that the Q prime, once you have reached 0 here, okay, so here the Q prime is counting down, even in this same circuit here. Notice that we jump back here to 15, from 0 back to 15. Okay, so once you reach actually here 0, 0, 0, 0, then basically you will jump back to 15. So notice that here, all of them will jump here to 1, 1, 1, 1 at the same time, because basically you are connecting here the Q0 prime back to the 0. So this is going to toggle, this is going to toggle. So you are toggling all of them. You are toggling all of them, and all of them will become ones at the same time. Right. So this is the ripple counter. This is the ripple counter. The timing of the ripple counter is a problem.
دكتور
محمد? Yes, محمد, تفضل.
في الكتاب he is connecting Q1 to the clock with inverted output with inverted wire يعني هل في الكتاب قصده انه up count بس نفس ال representation اللي موجودة الحين؟
Let me quickly check this for you. Just one second. Just one second. Let me just stop the pen tool here. You want me to check the textbook? Just one second.
Yeah.
Give me 1 second. على فكرة, it's the same ripple counter, but sometimes the drawing actually slightly differs. But the concept is still the same. But let me show you the circuit diagram in the textbook. So we have with D flip-flops and we have with T flip-flops, right?
Yes.
So let me show you this. Can you see the textbook? Can you see the textbook? Okay, is this clear? Yeah, let me. Type. So notice that actually in textbook he showed actually A0 on top and A3 at the bottom. So basically, and I showed it the other way around. I showed actually A3 on top, Q3 on top, and the Q0 at the bottom. So notice that the clock here, okay, so that's basically is the clock. The count here is the clock, which is connected to the clock input. Again, he's using negative edge. I'm using positive edge. It does not really matter. This is actually edge triggered flip-flops. So notice that how he's connecting, okay? So this is actually is with D flip-flops. This is with T flip-flops. He's using actually two different implementations, and I showed the D flip-flops, but you can also implement it with T flip-flops because the T is going to toggle. It's the same concept, okay? And he's actually connecting here the Q prime back to the D, the Q prime back to the D. And he is connecting this A to the clock, okay? But notice that how the clock is inverted, and I did not use the clock which is inverted. And I used actually a clock which is using the positive edge. He's using a clock which is negative edge. So notice that how he's actually playing with things in the textbook. You understand this? Yani, when actually I use actually Q prime to connect to this, I'm using a positive edge triggered flip-flop. He is using actually Q with a negative edge triggered flip-flop. It does the same thing. So when you use actually A here with a negative edge trigger, you see in design there is no unique solution. Don't memorize textbooks. This is bad because textbook is going to tell you one way to think, and I really would like you to think in a different way. So again, let's understand this. First, we are taking the Q prime and we're connecting it back to D so that we can toggle the outputs. So everyone is connecting Q prime back to D. But notice that he's using actually A0 to connect to a negative edge. I did not really use negative edge triggered flip-flops. I use positive edge triggered flip-flops. And I did not really use actually Q. I use a Q prime to toggle. Okay? It will have exactly the same thing. I use positive edge. No. Both of them are going to count exactly the same way. Both of them are going to count up. In the textbook, he's actually using a negative edge to connect to Q0. I'm using a positive edge and connecting to Q0 prime. Okay?
Okay.
And you will find that in different textbooks which are written by different authors, everyone does it differently. Okay? You can actually use a Q0 prime. So when a Q0 prime, when a Q0, notice that here when a Q0 goes from 0 to 1, let me show it to you again. Notice that here when Q0 goes from 1 down to 0, this will go from 0 to 1. We can actually have used actually here a negative edge triggered flip-flop and use actually when a Q0 goes from 1 down to 0 to actually to toggle the value of a Q1. It's the same thing. Yani, if I want to change this, so this is why if I want to change this to a negative edge, put a bubble here, then I have to connect Q0 here. I have to connect to Q0, not to Q0 prime. Q0 prime will be connected back to the 0, but I have to connect to Q0 and actually put an inverter here so that when this changes from 1 down to 0, we toggle. Okay, so we change the value of Q1. And I use Q1 prime, Q0 prime, sorry, to connect to the clock. So that to avoid putting a bubble here at the clock input. Is this clear?
Yeah, Rector, but if we don't use the inverter, we don't use the negative edge for Q0, and we connect Q0.
So if you are using a positive edge, let me put it this way. If you are using a positive edge, okay, trigger the flip-flops, then you have to connect Q0 prime. If you are using a negative edge and you would like to count up, right? We don't even want to change the counting, just we are going to count exactly the same thing. Then you have to connect Q0 to a negative edge triggered flip-flop. It will have exactly the same effect. So here, when I use a Q0 prime, okay, so when a Q0 goes from 1 down to 0, Q0 prime is going from 0 to 1, and this is why we are using the rising edge. Whereas if I would like to use the negative edge, then just use a Q0. Okay?
Okay.
So don't be confused. Don't be confused if you see actually different diagrams. Just understand that there are different implementations of the ripple counting. So I'm glad I'm showing you here a different implementation, okay, than the one which is used in the textbook, okay, which is using actually a positive edge, not negative edge. And in the exam, if you actually get the question how to implement the ripple counter using a positive edge, you already know how to do it. Because in the textbook, they showed you how to use a negative edge triggered flip-flops to implement this. So just change it from negative to positive and change the clock here from Q0 to Q0 prime, as shown in this slide. Okay, clear? Is this clear? Now let me show you something which is not really shown in the textbook. Yani I have seen many different textbooks, okay? So for this reason, I don't really follow one author. Yani I'm not really actually a copycat. I don't really copy what exists in a given textbook. And if the author puts actually something like this, this is not the only solution. There are actually different solutions. Right. So, so this is the timing of a ripple counter. This is the timing. And notice that how the clock is actually changing. So this is my clock. Notice that how Q0 is changing. So Q0 is, there is always a delay in the flip-flops. So at the rising edge of the clock, notice I'm using here the rising edge, not the falling edge. Okay, the author actually is using the negative edge, not the rising edge. So this is why I prefer to use the rising edge to explain this. So notice that the value of the Q0 is going to toggle at the rising edge. Okay, so there is a small delay. Now, because there is a small delay in a Q0, there is also a delay in a Q0 prime. Now, there is actually a second delay for any Q1 because we are using Q0 or a Q0 prime to toggle Q1. So we get actually a second delay. And then we are using Q1 prime to toggle Q2. So this is why we get a third delay in the Q2. So notice that how the delay is increasing. So here, actually, it was just the small delay from the rising edge. That's the delay in the flip-flop. Now we got two delays. because here we have the delay of Q0 and the delay of Q1. So we add the delay, right? And then we have 3 delays, because now we are using Q1 prime to toggle Q2, and we have a delay in Q2. So now we have 3 delays. And notice how the delay is going to increase in Q3. So basically, this is going to increase. This is why it's called a ripple counter, because the flip-flops are not driven by the same clock. Okay? They are not really driven by the same clock, and it's not really synchronized with the same clock. So the Q delay is going to increase as we go from Q0 to Q3. And this is why, because the delay is going to increase. So notice that if we say that delta here is the delay of a flip-flop, then notice that, okay, the delay of Q0 will be just delta because it's driven directly by the clock. Whereas the delay of Q1 will be 2 delta, because first we have to change Q1, and then after changing, notice that here when Q1 goes from 1 down to 0, we change Q2. Notice that here when Q0 goes from 1 down to 0, we change Q1. Okay. And here when Q1 goes from 1 down to 0, we change Q2. And when Q2 goes from 1 down to 0, we change Q3. So this is the rippling effect. This is my rippling effect. So this is why the delay is going to increase as we go from one flip-flop to another. So we start at delta, then 2 delta, then 3 delta, because every flip-flop has a delay. And this is going to increase the delay of the outputs Q0, Q1. So as we go from Q0 to Q3, the delay is going to increase. Okay. So to summarize, this is actually the drawback of the ripple counter. So very quickly here, I showed some differences. I showed here that in my drawing, I showed the Q3 on top. I showed the Q0 at the bottom. Okay, so Q3 is the most significant bit. Q0 is the least significant bit. Let me just here go back to the author textbook. Do not be confused. Okay, the way that the textbook has done it is that A0 is shown on top, A3 is shown at the bottom. This is the same ripple counter flip-flop. Okay, this is actually my ripple counter flip-flop. This is ripple counter. Okay, implemented using D flip-flops. Notice that always we connect the Q prime back to the D input. So this is Q0 prime back to D. This is Q1 prime back to D. Okay, this is actually for the toggling effect because we would like to toggle. The difference is that here he's connecting A0 to the clock input, but this clock is negative edge trigger. And I'm connecting the Q prime to the clock input, but it's actually a positive edge. It will have the same net effect. But in my case, I changed the state at the rising edge. In the case of the textbook, he's actually changing the state at the negative edge. So it depends on the flip-flops. If you are using a negative edge triggered flip-flops, you connect the, okay, like in this case, in the textbook. Okay, if you are using a positive edge, you have to do it the way it's actually described in my slides. Is this clear? Now, one thing which is shown in the textbook, okay, which is this diagram, is that you can also use the T. Okay, notice the T here. Okay, that's always connected to logic 1 because we would like to always toggle. That's logic 1. That's basically using the T flip-flop too, but the T flip-flop is more expensive than the D. So, and I prefer the one which is shown on the right because we are not really using a more expensive T flip-flop that has XOR gates, and this is always connected to logic 1 because we would like always to actually toggle. Okay, so in order to toggle here, rather than connecting this to logic 1, I can actually connect here the Q prime back to the D. That will have the same net effect. Okay. So these are two different implementations. Either you can use a T flip-flop that will always toggle. Okay, this is why the T input is always 1. Or you can use a D flip-flop. That's actually more interesting because we are connecting the Q prime output back to D so that we can toggle. I hope this is clear. If you want to spend more time on the ripple carry. Okay, this is not the ripple carry, the ripple counter. Okay. Any question about this? So there are many observations. You can actually change it in many ways. Okay, this ripple counter. Okay. Right.
Doctor, can we have like a counter with a news state?
With what?
A news states.
That will be very interesting. Okay, that will be very interesting, but I will not do it for the ripple counter. I will do it actually for the synchronous counter. So the ripple counter is very simple. It does not use any external gates, but it has a big disadvantage. It has a big disadvantage. It's not synchronized. Okay, so the flip-flops are not, so the clock is not connected to the clock input of all these flip-flops, and this is going to increase the delay of the Q output, so it's going to increase as we go from one bit to the next bit. So you can see that we have seen here that the delay can go from delta to 2 delta to 3 delta to 4 delta and so on. Now, how can we design a counter that can actually have like a certain sequence? I'll talk about this. Okay, so I need to talk about synchronous counters first. Okay, so here we would like to avoid the clock rippling. By the way, did you see the counters in the lab? Maybe you already have seen that, right? Students, have you seen the counters? Have you seen the counters in the lab? Okay, this is why you have actually excellent questions today. Okay, probably have seen it the way it's in the textbook, but you don't really see it my way. Okay, I'm actually showing it differently, so don't be confused. Do not be confused, okay? So I'm just showing another way, So this is why it's good to see that we have different ways of implementing the counter, okay? So it's good actually to know, in addition to what you have seen in the lab, so it does not have to be the way it is shown in the textbook only. No, there is no unique solution to a problem. There are many different solutions. As an engineer, you can look at this solution, at that solution, and then you can compare. That's actually will be something which is good. If somebody tells you that this is the only solution, no, he's actually making a big mistake. Okay, we can actually come up with other solutions as well. Let me talk about synchronous counter. Now, the synchronous counter, it will avoid the clock rippling. So the major drawback of the ripple counter is the rippling effect. So we don't really want to delay the output to Q when we go from one bit to the next bit. So as we go to the most significant bit, this is going to increase the delay. So we don't really want to have this. So we're going to have an n-bit register. So notice that how I'm drawing it, very simple. An n-bit register. So basically this n-bit register here, this n-bit register will consist of n flip-flops. Okay. We have the clock here, which is connected to all the flip-flops. So this is why it's truly synchronous. So this is why it's called synchronous counter. And also we have a reset initially because we would like to reset the Q output. So because we have an n-bit counter, we can start from 0 to 2 to the power n minus 1. So notice that this is my Q output that consists of n bits, n minus 1 down to 0. Okay. Now, in order to count up, I'm going to just use an incrementer, an n-bit incrementer. So the n-bit incrementer is going to just to add 1. Okay. It's very simple. It's very simple. It's not really that difficult at all. Okay. Do not be confused about diagrams and it has to be this way. Khalas, la. Okay. So we are going to design a very simple synchronous counter. And this incrementer takes the Q and add +1. That's it. And this will provide the next state. So the next state appears at the input of the n-bit register. And at the edge of the clock, okay, we just change the count. That's it. Okay. Now, this n-bit incrementer is going to look like this. So notice that the n-bit register, this is actually for a 4-bit synchronous counter. I'm using 4 flip-flops. Notice that the Q0 is my least significant bit. My Q3 is most significant bit. And this is a 4-bit counter. Notice how the clock is connected to all the flip-flops, all of them. Okay, so this is truly synchronous. So all of them, their Q output at the same time. So if there's a delay inside the flip-flop, which is delta, all of them will use the same delay. So all of them will change at the same time. That's the nice thing about the synchronous counter, because we are connecting the clock to all the clock inputs of all of these flip-flops. Now, all what I need is a 4-bit incrementer. Now, the 4-bit incrementer is just an adder that will add +1. That's the 4-bit incrementer. I have here added an enable input. Now, if this enable input is equal to 0, yani I would like to disable the counting, then basically we're adding 0. So this will not really change the value of, so the D will be equal to the Q. So if this enable equal to 0, so basically I'm going to XOR with 0. I'm going to get all of these carries are equal to zeros. And therefore, when I XOR with 0, basically the D will be equal to identically to Q. So D3 will be Q3, D2 will be Q2, D1 will be Q1, and D0 will be Q0. So there is no change. There is no change in the count, in the counter. So I can freeze the counter if enable equal to 0. If I would like to count up, I'm going to make enable is equal to 1. By making this enable equal to 1, basically I'm adding 1. So this is an adder that will add this enable. So it's just plus 1. That's it. Okay. So notice that how it's implemented using a 4-bit incrementer. And therefore, the value of D, D3, D2, D1, D0, it will be Q plus 1. And therefore, next cycle, we are going to just to increment the counter to become the value of a Q plus 1. That's it. Okay. And all of them are going to change at the same time. Now, this is a very powerful, very useful actually counter. I will show you actually how we can use this to build large counters. I will talk about also the different types of counters that exist in the textbook, but remember this slide, okay? Remember this slide. So that's it for today. Let me stop recording.